Welcome back. There's going to be a little bit of a mix. So instead of Milica, we'll have Aleksandar Veljkovic. He's a senior researcher at ATIC 42, and Milica will be presenting later on today. Aleksandar talks about privacy, presenting computation in plain sight, addressing one of the most pressing challenges in Web3 technology, balancing transparency with privacy. He'll explain how advanced cryptographic methods like zero-knowledge proofs and fully homomorphic encryption enable secure computation without compromising data privacy, paving the way for the enterprise applications in the decentralized world. Aleksandar, your turn.
Yes. Cool. Okay, hi everyone. I'm Aleksandar. I'm lead researcher at 3327, and that's R&D department of ATIC 42, but also MVP workshop. Besides that, I'm assistant professor at School of Computing, Union University. And today we'll talk about privacy preserving computation in plain sight. So what the hell is that? Well, the idea is to have a computation that anyone can observe, but no one can leak any private information from that. We'll run through several scenarios where you can see some basic patterns of, the example will be on AI model training, but you'll see basic patterns on how we can organize data, where to put the borders between users and owners of data and owners of models, so we can protect the privacy there. So first, let's just say two basic things so we don't get lost into the presentation. So first thing, what is the model? So what is the model type actually? In our case, it can be basically anything. So in fact, we can even remove AI as a word and put anything, any computation in the middle, and it'll still work. So for the model type, imagine it can be any type of model. It can be a discriminative model, generative model, doesn't matter. But also we have model parameters which define the model. So for neural networks, it could be weights or structure. So those are two things that you just abstract totally. First, let's see some basic patterns. So first you have data, of course, and you have model parameters that are trained on that data. On the other side, you have a client. The client sends a query, gets the result back. So what can be the query and what can be the result? Well, it depends on the model, but basically we can think about it as a prediction. If it's a prediction model, the discriminative model, it'll be some kind of prediction. If it's a generative model, it'll be a new instance. In some cases, you can even get for the result a model itself. So you can send the data and get the model back. Okay, so what is the issue here? Well, if we introduce another actor, we call it eavesdropper. Let's say what eavesdropper can leak from, which information can the eavesdropper leak, observing different parts of the system. So if he looks at data, of course it will leak sensitive data. So you can imagine it being hospitals and different medical institutions where you store sensitive data. If anyone eavesdrops the data, you'll get insights of that. Second thing, if the eavesdropper looks at the model parameters, what's lost? IP. So if you own the model and you want to sell that as a service, if someone sees your model parameters, you'll lose your intellectual property. Finally, if someone looks at the client, well, again, user data, sensitive data. So what is user data here? Well, imagine again being the hospital on the left side. If you ask the hospital engine, so these are my symptoms, what is wrong with me? And you get the result back. The other side, if anyone actually can see your query, that means that they will know what query you're sending, which means that you're leaking your own sensitive data. So basically, eavesdropper can learn a lot by just observing different parts of the system. So what can we do then? Well, let's see the first scenario. The first scenario is the basic scenario of any cloud service. On the other one side, you have a client. On the other side, you have a system owning data and owning parameters. The purple, that dotted line, is just a border of visibility. So left side cannot see the right side and the opposite way. So if the eavesdropper is on the right side, well, eavesdropper doesn't learn basically anything. Because what we can also do, we can encrypt query and decrypt results. If you use HTTPS, that's by default, but let's imagine that we added something there. But how can we trust the results? So what does that mean? So if you want to buy the service from a service provider, and you just send a query and get the result back, if you don't have any insight in the model, well, It can be basically anything. So you have no idea what's on the other side. You can pay for machine learning model based on artificial neural networks, and the other side you'll get some decision tree classifier that will give you some results. And you need to trust that the other side really spend their time and money to compute the model, but you have no clue. Also, the other scenario is when you want to train your data model. So you send the data to the service and get back the model. Again, if the eavesdropper is on the right side, you send the data encrypted, you get the model in encrypted form. That's fine, but if the eavesdropper is on the other side, well, you'll see your data. So what this basically means, even though it's not in AI domain, so it means that, for example, if you're logging on a website, you're sending your password to the other side and you're trusting the other side that they will store the password securely, hash it, and destroy it. Basically, they don't save it in plain text. But that means that you're really trusting some administrator on the side or I don't know, intern that will see the logs and say, okay, I will not save this. But that is the obvious problem with this kind of system. So organization itself can see the query data. Scenario 3, okay, let's put the border on the left side. So let's imagine that the client is sending encrypted queries or not encrypted queries because now parameters are visible, which means that parameters are on the client side and data is on the other side. Cool, now we can run the model, but what's the problem? You cannot sell the model because it's not intellectual property anymore. And again, source of data is unverifiable. So it can be a machine learning model based on artificial neural network, but it can be trained on crap data. And at the end, if you are the one who needs to compute everything, then you need to do heavy lifting. So if it's a complex model, you still need to do something. Scenario 4, okay, let's now reveal the data, give it to the client, and let the client trust that the model is trained properly. So the model is now hidden only. Intellectual property is saved, but sensitive data is revealed from the data set. If the data set is open source, we're good, but if the model is complex, it's not feasible for you to verify that you can train the same model from data. But on the other side, if you are able to train it, then you really don't need a model at all. So if you train it locally, you can use your own local instance. Now let's see some cryptographic tools that can help us with these scenarios to fix at least some of the problems. We'll look at high-level systems, so we'll not go into details. The most important thing here is to understand what it does, not how it works, because each of them are lecture themselves. So the first thing, cryptographic commitments. It's a simple thing, but pretty useful. So what does it mean? On the left side, you have your data A. So that's a value of A. On the right side, you put a commitment of for A. This means that you're locking your A in some kind of a box. Then that box has some properties. So it needs to be hiding, which means that if you are sending anyone your commitment, no one can determine what's inside. The best example to represent it is a hash function, but it's not really a hash function that's doing commitment, because if you're trying to hash values between 1 to 10, it's not really hiding if you can brute force it. So it means that the entire schema consists of hashing and something else. But just for the sake of understanding, you can think of it as a hash function. The other property is binding. So if you change your data somehow, the commitment is not the same. So anyone can say that you tempered something. Next, zero-knowledge proofs. What is that? So you want to prove the truthfulness of a statement without revealing any inputs, which basically means I can convince you into something by sending you my evaluated function of input data and also prove that my computation is correct. So how do we do that? We represent the computation as an arithmetic circuit and try to prove that based on some private inputs, we'll get public outputs. And if anything you should understand in the sense of zero-knowledge proofs is that you're not trying to prove the computation itself. You want to prove the consequence. And that's the key thing to understand about zero-knowledge proofs. Let me give you an example. So if I tell you I can distinguish between these two circles, these two items, basically you can see them as the same circle, but I say they're different. So how can I prove to you that I know the difference if you don't see the difference there? So you can take two items, let's imagine them as some spheres, you put them behind your back, you shuffle them, and you ask me again, did I shuffle them? If I say yes, and it's correct, cool, I guessed it. It's 50-50 chance that I will guess. If not, I messed up. So, but if we repeat the same process all over again 100 times, and every time I know that I guess correctly that you randomly shift your items from left to right hand, then probably with high probability I know the difference between the items, even though you cannot see it. So you see that I am proving consequence instead of proving the computation. I'm not proving that the sphere is white, there is small dot on the left side. I just prove that I know that. And finally, homomorphic encryption. That's the cool thing. So you have the value A, value B, and you encrypt the data. What you can get with homomorphic encryption is that if you sum encryption of A, encryption of B, I will end up with something that represents encryption of A plus B. Same for the multiplication. Now the plus and the multiplication signs are different colored because it doesn't really mean that it will be addition. It means that it will represent operation of addition in some domain. In some domain, let's say these are encryptions of Boolean values 0 and 1. On the left side, it can be an arithmetic addition. On the right side, it can be Boolean AND. And on the multiplication side, it can be, it's plus and or, multiplication and AND. What does this allow us to do is to create models and work on encrypted data directly. So I send encrypted data, perform computation, and return back encrypted results. So basically, the service provider is just a machine that runs dummy operations without any knowledge of data itself. And garbled circuits. These are weird concepts, but they're pretty useful because they are actually origin of other models like zero-knowledge proofs and homomorphic encryption. It's an MPC protocol where two or more participants together try to compute the value of some function without revealing anyone's inputs. So, as an example, I own the key, you own the data, and together we compute encrypted value of encrypted data, and no one knows anything. You don't know my key, I don't know your data. Now let's see how we can apply this to scenarios. So the first scenario was service provider, cloud service provider. What we can do, we can commit to parameters, hiding and binding commitment. We can generate execution proof, which says, I used your user query, and I ran the model with values that I used for commitments. So it's basically like a glue between everything, and I leak no information because I just send you the proof. Yep, you asked me for data, and I give you back the proof that I did it properly. It doesn't even have to be encrypted because eavesdropper doesn't learn anything. How efficient is it? Well, it depends what you want to do. So it is more expensive, absolutely, than just running the model, but it will give you something that you didn't have before. So in other words, if you want privacy, this is how you get it. There are already interesting libraries that will provide this for especially artificial neural networks, but also for any other model. Let's see what fully homomorphic encryption can help us here. So the other problem was that a service provider will see your query and learn from the query. Well, you encrypt the query using homomorphic encryption, you generate results on encrypted data using homomorphic function, and at the end you send the encrypted result to the user decrypts it. In this example, it's a symmetric encryption schema, so you have only one key, but in the middle, if I don't go into details, it will sound weird, but during the process, you can change the key several times. And now you'll send encrypted results, encrypted query, encrypted results, but not in the sense that the communication is encrypted, but the data itself is encrypted. And you can compute it. How efficient is this? Well, again, it depends, because there are different schemas. If you know that your computation will not be very, you know in advance how long the computation will take, the circuit of that computation is fixed, well, it can be pretty efficient using some scale schemas. If not, you're using bootstrapping schemas, but in other words, again, you get something that you didn't have before. It's not optimization, it's a new feature. Let's see scenario 2. So I send the data, you give me back the model, and the eavesdropper is on the query, is on the server side. Again, we can do fully homomorphic encryption to perform a training instead of inference. And again, you'll get the results of your model, but no one in the middle will know what happened. Just work on encrypted stuff. How can we prove the parameters? Which means that how can we say that, yeah, this model is really trained on some data? Well, again, we can use both ZK or FHE. So let's try something like this. We can commit to data, which means we cannot change the data anymore. We publish that commitment publicly, let's say on a blockchain. We also train the model. We commit to model parameters and create the two zero-knowledge proofs. One proof is that data is I say two proofs, but in general it can be unified as one proof. We create a proof that we train the data, that we use the data and create the commitment properly. So you can imagine it as a root hash of a Merkle tree, for example. And we can create a proof that we use the parameters properly that were committed to, initially, and publish that publicly. On the other side, we can send the query to the system, and the system can prove that it used the same values that are committed there. So we commit in advance, do the computation, and prove that we use those committed parameters for our computation. There are a bunch of optimizations, so even in this case, it can be efficient. Also, if we want to just do the computation with FHE, we can encrypt the results, encrypt the query, get the encrypted results on top of that. The holy grail will be to use both ZKP and FHE, but that will be inefficient so far. Now, this is an interesting thing. So, isolated silos. On the left side, there is a hospital, and in the middle, there is an organization who wants to train the model without seeing the data. So, hospital doesn't want to give the data, and the service provider wants to use that data to train. Well, we can do something like this. Actually, there are different things. Organization A can even do the same thing, but in this case, we explicitly want to say there are two organizations, and first organization really doesn't want to train the model. So organization B can interactively, using zero-knowledge proofs, communicate with organization A and interactively work together to train the model. Organization B at the end is sure that the model is properly trained. They can also commit to their values like data commitment and parameter commitment, and everything is the same on the right side. They will receive ZKP, that the model is trained properly, and the results are computed using the same model. And finally, multiple private silos. So you have two organizations with data, and they don't want to share anything, but they want to do it together. So one example is, the common example for this pattern is, let's say we are trying to, there are two organizations, one has a list of users, the other organization has also a list of users, and they want to provide some special benefits to other users of the other organization. So I like to give the coupons for everyone that also bought something from organization A. But organization A doesn't want to reveal the list of users, and organization B also doesn't want to reveal the list of users. What they can do, they can encrypt the data and encrypt the circuit and create a garbled circuit, which means that A generates a garbled circuit, which basically means encrypted circuit, encrypts the inputs. B is the evaluator, so evaluates the circuits, adding its own inputs, and together they will compute the final result, which is just result of whatever the operation was. In our case, it's a list of, it's a subset of all users. Basically, it's an intersection of sets of users on both sides. And it will look something like this. So with garbled circuits, we can even achieve that. So nothing is leaking and everything is computed properly. What we can see is that we have some issues. So it's convenience versus privacy. If we want convenience, we'll use cloud service. And that's something that we'll use. But if we want privacy, we'll need to think about some of the systems that we saw today. Performance, yeah, it is a trade-off. So you evaluate how efficient you want this to be, basically by telling yourself, this is how much I want to go further with that. So if you want to do, I don't know, one-time computation once a day, for example, that's perfectly fine. You can use whatever we saw today. But if you want to have a real-time service, then you need to figure out how to optimize everything and to provide the service. Again, it's not impossible. It can be implemented. And finally, as you saw, as I mentioned before, it's not just optimization of something that we already have. It's new scenarios. So you enable new use cases with cryptography. And even though they're not highly efficient, they're efficient enough so they can provide the services, especially in decentralized systems where this is the only way to work. And how is this related to something that we work in 3227? Well, we did a bunch of things, especially in ZK domain. So low-level things like implementing implementing library for converting, library for the sklearn library for multi-layer perceptron, we implemented a small modification that we can also add a verification on top of that, so you can get the results. We also did implementation of that library in Noir, in Cairo. Those are all ZK-related languages. Low-level constraint optimizations with Rust and ArcWorks. We also use Circum a lot. We worked on several grants. 2 of them are pending. 2 of them, specifically in this domain, just 2, are for Ethereum Foundation. Also, there are many ZK applications that are for the client. And we will not discuss who is the client because I'm behind the NDA. But overall, there are interesting applications like verifiable credentials. So I can prove that I own credentials with specific requirements without revealing anything. I'll just reveal the proof that I'm eligible to do something, for example. Or we're working on libraries for simulating ZK circuits and everything. So basically, a lot of ZK stuff, but also homomorphic encryption and everything you saw before. And what we offer: consultancy services, architecture design, implementation, education, especially education. A colleague of mine, Maria, is working a lot on the education stuff. She's assistant professor at Faculty of Mathematics. So she also gives courses on ZK. So if you're interested, feel free to contact us. And that's about it.
Thank you, Alex. Does anybody have any questions for Alex? Going once, 2 times, 3 times. Thanks, Alex.